In this video, we will be focusing on atomic structure models and line spectrum of hydrogen atom. What is atomic model? An atomic model is a theoretical framework that describes the structure and behavior of atoms. These models help scientists understand how atoms are composed, how electrons are arranged, and how atoms interact with each other. Over time, several atomic models have been proposed, each building on the previous ones to provide a more accurate and detailed understanding of atomic structure. What are main atomic models? Thomson's Plum Pudding Model, proposed by J. Thomson in 1904, following his discovery of the electron in 1897. Rutherford's Nuclear Model, proposed by Ernest Rutherford in 1911, following his famous gold foil experiment. Bohr's Atomic Model was proposed by Niels Bohr in 1913. Quantum mechanical model, the most advanced model developed in the 20th century, describes electrons as existing in probabilistic clouds or orbitals rather than fixed orbits. This model incorporates the principles of quantum mechanics to provide a more accurate and detailed understanding of atomic structure. What is Thomson's Plum Pudding Model? J. Thomson's model, proposed in 1904, depicted the atom as a sphere of positive charge with negatively charged electrons embedded within it like plums in a pudding. What are the limitations of Thomson atomic model? Thomson introduced the concept of positive charges just to keep the atom electrically neutral, but the presence of positive charges were not discovered by then. The model could not explain certain experimental results, such as the scattering of alpha particles observed in Rutherford's gold foil experiment. What is Rutherford's nuclear model? Ernest Rutherford's model, proposed in 1911, introduced the concept of a dense positively charged nucleus at the center of the atom, with electrons orbiting around it. This nucleus contains most of the atom's mass. The electrons orbit the nucleus at relatively large distances, similar to planets orbiting the sun. Most of the atom is empty space, which explains why most alpha particles passed through the gold foil without deflection. What are the limitations of Rutherford model? According to classical physics, electrons orbiting the nucleus should continuously emit electromagnetic radiation, lose energy, and eventually spiral into the nucleus. This would make atoms unstable, which contradicts the observed stability of atoms. The Rutherford model could not explain the discrete spectral lines observed in atomic spectra. It suggested that electrons could have any energy while orbiting the nucleus, but experimental evidence showed that electrons occupy specific energy levels. The model did not explain how electrons are distributed in different energy levels or shells around the nucleus. What is Bohr's model? Niels Bohr's model, proposed in 1913, introduced quantized energy levels for electrons, explaining the stability of atoms and the discrete spectral lines observed in atomic spectra. Bohr proposed that electrons orbit the nucleus in specific fixed orbits or energy levels. These orbits are quantized, meaning electrons can only occupy certain allowed energy levels. Electrons in these quantized orbits do not radiate energy, which addresses the issue of electron stability. As long as electron remains in a specific orbit, it does not lose energy and spiral into the nucleus. Electrons can move between these energy levels by absorbing or emitting energy in the form of photons. When an electron jumps from a higher energy level to a lower one, it emits a photon with energy equal to the difference between the two levels. This explains the discrete spectral lines observed in atomic spectra. What are limitations of Bohr model? Bohr's model could not explain the behavior of electrons in atoms with more than one electron. It worked well for hydrogen but failed for more complex atoms. While it explained the spectral lines of hydrogen, it could not accurately predict the spectra of large atoms or account for fine structure and the splitting of spectral lines. Bohr's model depicted electrons as orbiting the nucleus in fixed paths, similar to planets around the sun. However, this idea was later replaced by the concept of electron clouds or orbitals, where the position of an electron is described by a probability distribution rather than a fixed path. The model could not explain the Lyman effect, which is the splitting of spectral lines in the presence of a magnetic field. What is quantum mechanical model? The most advanced model, developed in the 20th century, describes electrons as existing in probability clouds or orbitals, provide a more accurate and detailed understanding of atomic structure. What was blackbody radiation issue? In the late 19th century, scientists were trying to understand blackbody radiation, which is the radiation emitted by a perfect black body. Blackbody is an idealized object that absorbs all radiation falling on it. Classical physics could not explain the observed spectrum of blackbody radiation, leading to what was known as the ultraviolet catastrophe. How Planck's theory resolved the issue of blackbody radiation. In 1900, Max Planck proposed a revolutionary idea to solve this problem. He suggested that energy is not continuous, but rather quantized. This means that energy can only be emitted or absorbed in discrete amounts called quanta. Planck introduced the concept that energy of electromagnetic radiation is proportional to its frequency. This relationship between energy and frequency of electromagnetic radiation is given by the equation E equal to h into nu, where E is the energy of the radiation, nu is the frequency of the radiation, and h is Planck's constant, which is equal to 6.626 10 to the power minus 34 joules second. What is atomic spectra? Atomic spectra refer to the spectrum of frequencies of electromagnetic radiation emitted or absorbed by an atom's electrons as they transition between different energy levels. These spectra are unique to each element and can be used to identify the presence of specific elements in a sample. How atomic spectra is obtained? Scientific procedure to obtain atomic spectra is an interesting subject of its own. Theoretically, when an atom absorbs energy in the form of heat or electricity or light, its electrons get excited to higher energy levels. Higher energy levels are not stable, and electrons wait for every opportunity to return to their stable energy levels. As the excited electrons return to their lower energy states, they release energy in the form of visible light or infrared radiation. This light is emitted as specific wavelengths corresponding to the energy difference between the excited and ground states. The emitted light can be passed through a prism or diffraction grating to separate it into its component wavelengths, providing a series of discrete lines known as the emission spectrum. By the way, each element has a unique emission spectrum like a fingerprint because the energy levels of electrons are unique to each element. What are the types of atomic spectra? Atomic spectra can be of two types: emission spectrum, produced when electrons drop to lower energy levels and emit light. It consists of bright lines on a dark background. Absorption spectrum, produced when electrons absorb light and move to higher energy levels. It consists of dark lines on a bright background, corresponding to the wavelengths of light absorbed. What is the line spectrum? A line spectrum is a type of atomic spectrum that consists of a series of discrete lines, each representing a specific wavelength of light emitted or absorbed by an atom. These lines correspond to the transitions of electrons between different energy levels within the atom. Line spectra are unique to each element and can be used to identify elements based on their spectral lines. What are important series of lines in hydrogen spectrum? The hydrogen spectrum consists of several series of lines, each corresponding to transitions ending at a particular energy level. The most well-known series are Lyman Series, which is observed when electrons make transitions to the n equal to 1 level, emitting ultraviolet light. Balmer Series is observed when electrons make transitions to the n equal to 2 level, emitting visible light. The Balmer series is particularly important because it falls within the visible spectrum. The lines in this series are named H alpha, H beta, H gamma, etc. and they correspond to transitions from higher energy levels where n greater than equal to 3 to n equal to 2 level. Paschen series is observed when electrons make transitions to the n equal to 3 level, emitting infrared light. The diagram shows spectral lines for hydrogen atom. There are 5 series of lines corresponding to energy level from 1 to 5 and corresponding spectral region from ultraviolet to infrared region. Notable aspect here is the Balmer series that falls in spectral region of visible range. What is the Rydberg constant? The Rydberg constant is a fundamental physical constant that appears in the Rydberg formula, which describes the wavelengths of spectral lines in hydrogen and other elements. It is crucial in the field of atomic physics and spectroscopy. For Balmer series, Rydberg formula is given by 1 by lambda equal to RH, whole multiplied by 1 by 2 square minus 1 by n square, where lambda is the wavelength of the emitted light. RH is the Rydberg constant for hydrogen, which is equal to 1.097 10 to the power 7 per meter. N is the principal quantum number of the higher energy level, n equal to 3 or 4 or 5. As an example, in case of hydrogen atom for transition of electron from energy level 3 to energy level 2, using the Rydberg formula, you will see that the wavelength lambda is approximately 656 nanometer, which corresponds to the red line in the visible spectrum of hydrogen. As an example, for hydrogen alpha line for transition from n equal to 3 to n equal to 2, 1 by lambda equal to 1 by 2 square minus 1 by 3 square, which is equivalent to 656 nanometer. This wavelength corresponds to the red line in the visible spectrum of hydrogen. Now it is the time for brain teasers. Yellow light emitting from a sodium lamp has a wavelength lambda of 580 nanometer. Calculate the frequency and wave number of the yellow light. The frequency of light is related to its wavelength and speed of light by the equation V equal to c by lambda, where V is frequency, c is the velocity of light, and lambda is the wavelength. Plugging in the values, nu equal to 3 into 10 to the power 8 meter per second divided by 580 10 to the power minus 9 meters, which is equal to 5.17 10 to the power 14 hertz. Wave number is the reciprocal of wavelength lambda, therefore wave number equal to 1 by lambda, which is equal to 1 by 580 10 to the power minus 9 meter, which is equal to 1.72 10 to the power 6 per meter. Teaser 2. What is the energy of each photon that corresponds to light of frequency 3 into 10 to the power 15 hertz? To find the energy of each photon, you can use Planck's equation E equal to h into mu, where E is energy of photon, h is Planck's constant 6.6 to 6 10 to the power minus 34 joules second. Plugging in the values, E equal to 6.6 to 6 10 to the power minus 34 joules second multiplied by 3 into 10 to the power 15 hertz, which is equal to 1.988 10 to the power minus 18 joules. Teaser 3. How many photons of light with a wavelength of 4000 picometer that provide 1 joule of energy? Given values are lambda equal to 4000 picometer, which is equal to 4 into 10 to the power minus 9 meter. Energy of one photon equal to E equal to h nu equal to h into c by lambda, where c is the velocity of light, lambda is the wavelength. Plugging in the values, A equal to 6.6 to 6 10 to the power minus 34 joules second multiplied by 3 to the power 8 divided by 4 into 10 to the power minus 9, which is equal to 4.9695 10 to the power minus 17 joules. To produce 1 joule of energy, number of photons required equal to total energy divided by energy of 1 photon, which is equal to 1 joule divided by 4.9695 10 to the power minus 17 joules, which is equal to 2.01 10 to the power 16. Teaser 4. If a 25-watt bulb emits monochromatic yellow light of wavelength 0.57 micrometer, calculate the rate of emission of quanta per second. Given values are lambda equal to 0.57 micrometer, which is equal to 5.7 10 to the power minus 7 meter. Energy of one photon equal to E equal to h into nu equal to h into c by lambda, where c is the velocity of light, lambda is the wavelength. Plugging in the values, A equal to 6.6 to 6 10 to the power minus 34 joules second multiplied by 3 to the power 8 by 5.7 10 to the power minus 7, which is equal to 3.49 10 to the power minus 19 joules. Power of electric bulb equal to 25 watts, which is equal to 25 joules per second. Therefore, number of photons emitted per second equal to 25 joules per second divided by energy of one photon, which is equal to 25 divided by 3.49 10 to the power minus 19, which is equal to 7.16 10 to the power 19 photons per second. Teaser 5. What is the maximum number of emission lines when the excited electron of a hydrogen atom in energy level n equal to 6 drops to the ground state? When an electron transitions from n equal to 6 level to n level below 6, total number of possible transitions are given by n into n minus 1 divided by 2. Therefore, number of emission lines equal to n into n minus 1 divided by 2, where n is the initial energy level of the electron. Plugging in n equal to 6, you will get number of emission lines equal to 6 into 6 minus 1 divided by 2 equal to 15. So maximum number of emission lines when the electron transitions from n equal to 6 to ground state is 15. Teaser 6. How much energy is required to ionize a hydrogen atom if the electron occupies n equal to 5 orbit? The energy of an electron in a hydrogen atom at a given energy level n is given by the formula En equal to minus 13.6 electron volt divided by n square, where En is the energy of electron at level n. 13.6 electron volt is the ionization energy of hydrogen, that is energy required to remove an electron from the ground state n equal to 1. Energy at n equal to 5 is equal to minus 13.6 electron volt divided by 5 square, which is equal to minus 0.544 electron volt. Required ionization energy is the energy required to completely remove the electron from the current energy level n equal to 5. Note that energy at infinity equal to 0. Therefore, ionization energy equal to E at infinity minus E at 5 equal to 0 minus 0.544 electron volt, which is equal to 0.544 electron volt. Teaser 7. If the mass of electron is 9.1 10 to the power minus 31 kg and its kinetic energy is 3.0 10 to the power minus 25 joules, calculate its associated wavelength. Given that kinetic energy equal to 3 into 10 to the power minus 25 joules and mass of electron equal to 9.1 10 to the power minus 31 kg, kinetic energy of the electron is given by kinetic energy equal to half mv square, where m is the mass of electron and v is the velocity of the electron. Therefore, velocity is given by v equal to square root of twice kinetic energy divided by m. Plugging in the values in the above equation, v equal to 8.1 to 10 to the power 2 meter per second. De Broglie wavelength is given by lambda equal to h upon mv, where h is the Planck's constant, m is the mass of electron, and v is the velocity of electron. Plugging in the values, lambda equal to 8.97 10 to the power minus 7 meters, which is equal to 897 nanometer. With this, we have reached the end of this video. See you in the next video of this series on quantum mechanical model of atom. If you like the video, please do subscribe. Thank you for watching.